Good afternoon. Let's now study about what's meant by magnetic flux. Okay. So the magnetic flux phi b through an area A in a magnetic field is defined as the number of magnetic field lines passing through that area normally. Okay. So I've written the definition on top. Let's see what does it mean. Okay. So they say magnetic flux. Okay. The symbol of a magnetic flux is phi b. Okay. So let's take a magnetic field here. Okay. So there's a magnetic field like this way. Like this. Imagine this is the magnetic field lines. Okay, we marked as B vector because magnetic field is a vector quantity. Now let's take an area. That area is kept at an angle to the magnetic field. See, like this way. This is an area kept at an angle here, like this way. Okay. Now we see. Let me take a textbook here, a physics book itself for a thing. Okay, example. So this is a book here. Now the book will have a normal. Okay, like this way. Normal is at 90 degrees to the plane of the book, like this way. You can see here. So at 90 degrees, okay, like this way I'll draw a normal here. This normal is n cap. Okay, it's a unit or normal vector we say. Okay. So magnetic field goes straight. Okay. This is a book here, and the normal is like this way. Okay, the normal is to the surface, not to the magnetic field here. Okay. So in this case, it makes an angle here. That angle is theta. The angle is theta. Now here we can define what is the magnetic flux here. The magnetic flux symbol is phi b, that's equal to integral of b vector dot dA vector, okay, over the area A. That's why it's here A here. Okay, b vector dot dA vector. So we have multiplied the b vector, this is the magnetic field, and dA means what? We can take small areas here, like this way. In this area here, we take small area, that is dA, like that way. Okay, then we can add everything and that will give us a total area. That's what we have the integration here. Okay, like this way it is. Now what we do now, we'll take a second condition here. Okay. The condition is that the surface is exactly perpendicular to the magnetic field. Okay. So this is the surface here. It is perpendicular to the magnetic field, exactly perpendicular. How would draw that? Like this way. Okay. This is the surface here, and this is the magnetic field. Okay. So surface is exactly perpendicular to the magnetic field here. Okay. So the normal, what will happen to normal? So normal will be like this way. The magnetic field also goes the same direction. So normal and the magnetic field are in the same direction here. So the angle between the two lines, that's normal and the magnetic field will be 0. So the angle here theta is equal to 0 degrees. Okay. So let's substitute this formula and see here. We know that phi b is equal to b integral of a b vector dot dA vector. We know that a vector dot b vector is equal to what it is? AB cos theta. Okay, very simple. So what we do is we now expand it. Okay, right here a b vector dot dA vector will be b dA cos theta. Okay, let me erase this now. Okay, erase this. Let me continue here this side. Okay, so what we do now? Magnetic field is a constant. Okay, cos theta also will be a constant, so we take it out. So we have here b into cos theta into integral of dA vector. Okay, a. Okay, the integral is a. So what we're doing is, I said now dA is a small element here, dA, the small area element. Let we add all the area elements, then we get here the total area. So that will be b cos theta into a. We can write a front itself. So we have here b a cos theta. Okay. Now we see the angle here theta is what? Theta is 0. Okay. Substitute here. What is the value of cos 0? Cos 0 value is 1. Okay. So we know cos 0 value is 1. So we get here b a. So in this case we have here phi b. Okay. So this happens when, this is the second condition, when the magnetic field is in the same direction, or when the magnetic field is perpendicular to the surface here. The magnetic field is perpendicular to the surface. In that condition, we will have this value here. But the general formula is this one only. Okay, this is the general formula. Okay, this is at an angle. Okay, but this surface is perpendicular to the magnetic field. Okay, so now we know these things. Okay, let me erase this part here. Erase it. Then now we'll see the SI units here. Okay, what is the SI unit of magnetic flux? Okay, the SI unit is, we say Tesla meter square. Okay, Tesla meter square. Tesla meter square. Okay. Sometimes we also measure in another unit called as Weber also. Okay. Okay, we can also write also measured in Weber. Okay. Weber. Symbol for that will be capital W and small v. Okay. Then 1 Weber it's equal to 1 Tesla meter square. Okay. This also you must note. 1 Weber is equal to 1 Tesla meter square. Thank you for watching. This is about the constant magnetic flux. Thank you very much.